all, I'd like to thank the organizers for inviting me to take part in this meeting. Today, I want to talk about a critical point of the affine area functional. The idea is to understand better the geometry and the main properties of this functional. The schedule for the lecture will be the following. First, a review of the affine area functional will be done, and we'll see how the critical point of this functional can be represented. I apply this representation to some symmetry properties and to describe helicoidal surfaces. At this point, we will study a critical point of the affine area functional admitting some kind of singularities. At the end, I pose some unsolved problems that I hope I consider they are interesting. Okay, so to start, let me remind you that the affine area functional is given by the expression here, where by Ke we denote the Euclidean Gauss curvature, and the Ea is the element of the Euclidean area. This functional has attracted many geometers since the beginning of the last century. The work of Blaschke from 1923 is especially interesting. He proved that the Euler-Lagrange equation of this functional is of fourth order, and it is equivalent to the vanishing of the affine mean curvature. It's for that he called this kind of surfaces affine minimal surfaces. But later, 60 years later, Calabi in 1982 proved that for the convex case, always the second variation is negative. So, in a good criteria, he proposed to call the family of affine maximal surfaces. Observe that in this equation here has a particular class of trivial solution. It can be obtained when omega here is constant. This trivial solution corresponds to the family of surfaces with parallel affine normal line. It's like the plane in the Euclidean case. But here the family is very large. Okay. Important contribution to the subject has been the discovery of a Weierstrass type representation for this family, which has been important in the description of new examples. Also, two very celebrated results has been the non-conjecture solution of the conjecture of Chern and Calabi. The first one say that the entire solution of the affine maximal equation are always quadratic polynomials. And the second one says that every affine complete, affine maximal surface must be always an elliptic paraboloid. Also, there exists a formulation of the affine plateau problem. This formulation was done by Rudiger and Wang in 2005. They studied they posed a geometric variational problem for the affine area functional, for which the system and regularity of the massive margins have been proved. All the research has motivated an important amount of research, essentially all of them follow two new research lines. One consists in extend the result to different nonlinear fourth-order equations, and the other one study the validity of the results in affine maximal surfaces with some natural kind of singularities. Okay, first of all, in order to understand how this family of surfaces can be represented, I'm going to denote by G a locally strongly convex immersion in R3 oriented so that the second fundamental form of the immersion is definite positive. The three most important affine invariants are the affine metric, also known as the Bergman-Blaschke metric, which is conformal to the second fundamental form, the equiaffine area element, dA, and the affine normal G, which is given by 1/2 of the Laplacian of the immersion with respect to the affine metric G. Geometrically, the affine normal can be seen in the following way. The affine normal line is the tangent line to the locus of the center of gravity of the parallel slices to the tangent plane at the point P. Okay, in affine differential geometry, there is an interesting normalization given by the affine conormal vector n, which is a vector always perpendicular to the immersion, and it is normalized so that the inner product with affine normal is always equal to 1. Then, using this basic notation, the Euler-Lagrange equation reads in a nice way, because affine maximal surfaces means that the affine conormal always is a harmonic map respect to when you consider the conformal structure induced by the affine metric G. So we have a beautiful way in order to obtain affine maximal surfaces is using harmonic maps. In fact, using the Lilium formula, we can obtain any affine maximal surface from a harmonic curve M in this way here. And the affine metric is given by this quadratic form here. It's clear that we need to impose to the harmonic curve that it is a star shape, because we need that this will be well defined of the surface. Some examples are the following. If we consider the plane harmonic curve M here, UV1, then we obtain the most easiest affine maximal surface, the elliptic paraboloid. And here we have another example of a rotational affine affine maximal surface given by this harmonic map here, well defined on a puncture plane. Okay, I will remark that if we start with a plane harmonic curve, always we obtain an affine maximal surface with all the affine normal line parallel. So the family is, as I mentioned before, very large. Another way in order to describe affine maximal surfaces is the affine Bjorn problem. If we solve this problem, roughly speaking, consists in the system and uniqueness of affine maximal surfaces containing a given curve with a prescribed affine normal along the curve. In order to understand that, if we consider an affine maximal surface Xi with affine normal Xi and affine conormal vector n, which is harmonic, then given any curve beta, if we denote by alpha, y, and u, the curve, the affine normal and the affine conormal along beta, then the equation here always holds trivially. In fact, the first equation and the third equation follow because alpha prime and b prime are always tangent, u is normal. The second equation is followed because the normalization of y and u, and the third equation comes because the affine metric is well defined along the curve. So the important thing is that these four equations let us to recover at least locally the immersion. So we are going to give the following definition. Given three analytic curves, y, u, and alpha, in R3, then we say that the pair yu is an analytic equiaffine normalization of the curve alpha if there exists a positive function lambda such that all the equations here hold. And then we have that always is possible to recover from these properties, from this equation, the immersion. Given any analytic equiaffine normalization of the curve alpha, then it's possible to get in a unique way an affine maximal surface containing the curve alpha with conormal fit and Blaschke normal fit along the curve u and y respectively. This affine maximal surface will be called the surface generated by the analytic equiaffine normalization u and yu. And the proof is not difficult. Really, essentially the proof comes using the inverse function theorem identity principle. In fact, using that, we can recover from u, y, and alpha the affine conormal in a neighborhood of the curve. So using the Lelieu formula, we obtain the immersion in a unique way. In particular, if we consider two analytic curves, alpha and y, satisfying the following equation here, then always it's possible to solve the Bjorn problem. In fact, there exists a affine maximal surface containing alpha with the prescribed affine normal, the curve y along the alpha. The proof is very easy. In fact, as E prime, alpha prime, and y are linearly independent, then it's possible to get in a unique way from the above equation u and lambda so that the immersion can be recovered using the corresponding affine conormal vector field in terms of the y alpha, in terms only of y and alpha along the curve. So that formula gives us also another way in order to represent the corresponding affine maximal surface. In this case, never the curve is an affine curvature line of the immersion because alpha prime and y prime are always two independent vectors. But if we look for the case that alpha be a affine curvature line, then we have the following result. Given also alpha and y, show that e prime and alpha prime are always proportional, then given any function lambda, it's possible to get also in a unique way a improper affine maximal surface containing the curve alpha, such that the affine normal along alpha is always the prescribed curve y. The proof, again, follow in an easy way from the above existence theorem, because in that condition we can represent u using only the curve alpha and the curve y. I also like to mention that for an affine maximal surface, we have the following property. If along our analytic curve the affine normal is constant, then always the affine normal must be constant. The affine normal must be constant everywhere. So in that situation, we have that only need that this vector be constant along a curve in order to get an improper affine sphere. In the case that the two vectors e prime and alpha prime will be proportional, but this determinant here is equal to 0, then if it's possible to get an affine maximal surface containing the curve alpha with prescribed normal y, then the solution is not unique, because there exist infinitely many affine maximal surfaces with this solution. Okay, this result can be applied in two ways. One of them is in order to obtain some properties, some symmetry properties. For instance, if we consider an equiaffine transformation T, we say that T is a symmetry of an analytic equiaffine normalization yu of a curve alpha, when the transformation here leaves invariant the data here. In that sense, there is possible to get an analytic diffeomorphism, show that this expression here holds. It's not difficult that the uniqueness in the above theorem gives us that any symmetry of an analytical equiaffine normalization induces a global symmetry of the affine maximal surface generated by the equiaffine normalization. And also, this can be applied in order to describe all the liquidal affine maximal surfaces. In fact, given any one-parametric subgroup of equiaffine transformation, then any heliquidal affine maximal surface can be obtained at the surface generated by the following affine equiaffine normalization, y and u along an orbit of a fixed point. Y and u are given here. So in that way, we can obtain all the heliquidal affine maximal surfaces, and some picture of them are the following. Here, the curve alpha is not an affine curvature line. Here we have another example with all the affine line parallel. In that situation, we obtain an example where the curve alpha is an affine curvature line. These are the rotational sphere. All of them have parallel affine normal line. Here are rotational affine maximal surfaces, which are not affine sphere. More examples. And at this point, I like motivated essentially by the previous picture. It is interesting to consider affine maximal surfaces admitting some kind of singularities. In fact, both examples, if you observe the both examples, they are glued by analytic curves, and along the curve, the affine conormal always is well defined. Moreover, all of them can be represented using the Lelièvre formula. So we can think in study some kind of singularities in this kind of surfaces, in this kind of affine maximal surfaces. In fact, we say that a map, sigma, from a Riemann surface is an affine maximal map if this can be obtained in the usual way from a harmonic map N from sigma into R3. We need to assume that the determinant here doesn't vanish identically in order to obtain in an open set a well-defined affine metric. In that case, we'll say that the harmonic curve M is the affine conormal of the immersion. The singular set of this map corresponds to the point where the quadratic form here vanishes. And it's clear that the complement of this singular set is a dense subset of the surface sigma. Then it's possible to motivate also the definition, because one can prove that essentially the singular set determines up to a function all the surface. In fact, given any function alpha, any regular curve, then there exists an affine maximal map containing this regular curve in its singular set up to an analytic function h. That can be proved from our previous result, because we can obtain u and y in terms always of the analytic function h and alpha. In both cases, when alpha has no vanishing torsion and when alpha is a planar curve. Okay, as in the regular case, we can think also in studying in a global way affine maximal map. That is, affine maximal surfaces with some kind of singularities. Roughly speaking, we say that an affine maximal map is complete when it is affine complete at the infinity. That is, when it is complete outside of a compact. In that case, using a classical result of Hoover, we can prove that any complete affine maximal map is always conformally to a compact Riemann surface with a finite number of points removed. This point will be the end of the map, and we say that an end is algebraic when the holomorphic one form here extends meromorphically to the end. We can study the behavior of the affine maximal map in a neighborhood of the end. In fact, if we consider an embedded algebraic end of a complete affine maximal map with conormal affine normal n, then always we can prove that P must be a pole of order 2 of this holomorphic one form here, and there exists always a coordinate so that the pole is of order less than 2. The proof is long, but it is straightforward computation using the Maclaurin series expansion of the harmonic function of a puncture disk. So it's not difficult to see. The first result that one can obtain in a global sense is the following. It's an extension of the affine Bernstein problem. If we consider a complete affine maximal map with only a unique embedded algebraic n, then it's possible to prove that the surface must be equivalent to the is an elliptic paraboloid. The proof can be done in several steps. First, as we have a unique embedded algebraic n, the surface is conformal with to a Riemann surface with a point removed. We study what happened with the holomorphic one form at the end, and prove that it's possible to get a harmonic map well-defined well-defined in the compact surface sigma. So it must be constant, and we obtain that the affine conormal must be a plane curve, and so we have an improper affine sphere. In that case, it's not difficult to see that the only possibility is to have an elliptic paraboloid. In a similar way, we can describe annular affine maximal maps. In fact, if we consider a harmonic curve n, the real part of this holomorphic function will define of a puncture plane, phi set as a set plus b over z plus c, where a, b, and c as vector in C3. Then a, b, and c can be chosen in order the following equation here hold. In fact, we have a well-defined Riemannian metric, a fine metric at the end, in a neighborhood of the end. The immersion will be well-defined also, and this formula also holds about the degree of the coordinates of the holomorphic function phi. Using this, it's not difficult to see that the map GABC given by the usual formula is a complete affine maximal map with only two embedded algebraic ends. And all the annular affine maximal maps can be constructed in this way. Here you have some picture of this annular affine maximal map. Some of them are rotational, like these two, or are not rotational. Then it's possible to prove that also in a global sense, any complete annular affine maximal map with algebraic ends must be affine equivalent to one of the maps described before. The proof also can be done as in the case of the previous theorem. I think I'm going to jump it because it's not difficult to see. Let me spend the last part of the talk in the study of some kind of singularities that doesn't take place in the minimal surface theory. This is the isolated singularities which are embedded in a neighborhood of the singularity. Here we have an example of a rotational affine maximal surface. And in that point, we have an isolated singularity because we can consider the upper one of the two parts as a graph of a puncture disk. And here at the bottom, it's difficult to see, but we have another isolated singularity. This, in that case, the surface always is a graph of a puncture disk, so the function is always a solution of the affine maximal equation, the equation of fourth order I talked before. And the situation is completely different in this case and in this other case. In this case, the normal is not well defined. So the conformal structure here is the conformal structure of annulus. But at the bottom here, at the singularity, the conformal structure is a puncture disk. And in this situation, we have a well-defined normal along it. So it's important to distinguish between the case where the conformal structure induced by the affine metric is a puncture disk or an annulus. In that sense, it's possible to classify when the solution of the maximal equation which are conformally a puncture disk, because all of them must be asymptotic to the rotational solution. It's like the picture here. All of them are in some sense next to this a rotational solution like this. But in the case that the underlying conformal structure will be the underlying conformal structure of an annulus, then we have many ways in order to construct isolated singularities. In fact, given any 2-pi periodic analytic parametrization of a strict convex Jordan curve and any 2-pi periodic analytic function lambda, then we have two ways in order to get solution. The first one is by considering the holomorphic maps here, well defined on this annulus, and then it's not difficult to prove that the real part of these holomorphic curves give us solution of the maximal equation on a puncture disk. This harmonic curve is the affine conormal vector field of the corresponding graph. Moreover, phi extends continually to the origin, so we have an isolated singularity, and the normal, when we normalize to height 1, tends to the convex Jordan curve gamma. So, given gamma, we have a lot of examples of isolated singularities. But there is another way in order to construct new example, different, not equivalent to this kind of example. In fact, now we can consider in this also now the following holomorphic curve G gamma lambda, well defined on the annulus nabla R, and we can prove also the existence of solution such that they satisfy the properties in the above theorem, in the previous theorem. So we have different ways in order to construct different examples of isolated singularities of the a fourth order equation, the equation of maximal surfaces. Let me end with some unsolved problems that I think can be interesting to study. Some of them, the first one is consists in extent, in some sense, the affine bursting problem. For instance, it's possible to classify global graph with, we can start with only one isolated singularity. We can think if all of the examples, there is rotational example, but they are all the examples can be rotational, I don't know. Or more general, it's possible to classify all the global graphs which are solution of the maximal equation with a finite number of isolated singularities. It also is interesting to classify the kind of isolated singularities that occur in a affine maximal map. We know, because about isolated singularities, we know that classification in the case of the conformal structure is a puncture disk, but until now is open the way that you can construct any isolated singularity which is conformal to an annulus. Finally, as I said before, should be interesting to know all the kind of singularities that you can find in an affine maximal map. That is all.